Oh shit, you wrote it right. You wrote it, you told me right. But I copied it probably.
Ik zit echt vast bij die quantum computing bonus.
Oh, ik heb er nog helemaal niet naar gekeken, joh.
Dat is echt vreselijk.
Ja?
Dit is TCS.
Oh, super, zo moet je doen?
Ja, alleen nu kan je geen antwoorden op internet vinden.
I just read on the I assume it was. And you weren't here last year when it was actually started.
It's not in fact selected 5 part 2.
Can we actually see our midterm before we have the exam?
Yeah. So I'm going to bring them to the tutorials today. Yeah, it wouldn't make sense not to see them.
Yeah, no, exactly. I was very happy with my grade, but it's still nice to see what we do.
Of course, yeah. Yeah, so I just haven't had a chance because I got flu, but I will put the memo up so you can compare.
Okay.
And then if you want to question anything, it's fine.
Yeah. Did you actually see my email about tutorial 3? Because I still cannot see it, but I'm not sure if you just didn't upload it.
I haven't actually had a chance.
Okay, yeah, no.
Yeah. I will go through the, I got flu on Friday.
Mm-hmm. Oh.
So I just was trying to get my notes ready for today, and we'll get there.
All-nighter on Friday. And afterwards,
Ja, joh, bijna niet.
Ja, super goed.
Ja, ik wil wel even een midterm. Zijn er eigenlijk nog meer aanmeldingen gelopen voor EDS?
Ik had net 1 keer gegeven, dus nu hebben we 2.
Twee mensen?
Het kan nog. Jij kan nog wel wat komen.
Ja, ik zou het op zich ook niet heel erg vinden als het niet doorgaat. Ik ben thuis, ik vind het echt fucking leuk, maar...
Ja, nu niet meer, want Albert Ross heeft nu een hele staatshoofd gekozen. En Ziegler van Engeland. En ik denk dat als we nu echt een regering maken...
Alright. So, as you all have seen, I managed to get the midterm graded. Yay! Overall, nicely done. You'll also have seen an announcement about the tutorials this afternoon. So, I think as some of you will know from last week, Gabrielle had to go back to Brazil unexpectedly. And I thought rather than trying to get someone to suddenly sub in this last week, I will just take all the tutorials. But that means we'll need to combine for the first tutorial Monday and Thursday. So please just, all the tutorials this afternoon will be in 0.001? Yeah. Okay. This floor. I think it's the
001.
I think it's the big one over there. Yeah. Okay. So we'll do that, and hopefully, so I'm hoping we'll get that on Thursday, but I'm just waiting to hear. Okay, but for today, this afternoon, 0.001. I will bring all your midterms so you can actually get them back, and then just check through, ask any questions, tell me I added up wrong, which is likely, even though I used a computer. Yeah.
You marked it too high.
All right, can I just do a quick check-in? Any questions, concerns about the course? All right, how's the workload going? I know that we're covering a lot. How are you doing? Great.
In math or overall?
Only over what I have some limited control over, so just the maths.
I mean, technically you have control over the rest.
How do I have control
Like,
over the rest?
you can control overall control by controlling the map.
True. Agreed.
Well, yes.
But
Yes. I mean, the maths controls everything, but yes.
Other courses
I mean, if we just program one
All right.
of those two.
Okay. So, we will probably do a little more content on Thursday, so do a similar thing to we did previous Thursday, but not for such a long, terrible lecture. Just finishing off the last little bits. So which will mean you'll have all the material by the end of Thursday, and then you have a week until the final. Okay. I will put all this in an announcement, but the final, so this is, I mean, as you've seen, each section that we do builds on the next one. So while I will say that the final will only cover the things since the midterm, obviously you're not going to be able to do that unless you kind of revise and fully understand the earlier stuff. But I'm not going to be asking questions from the first couple of chapters, but I will put all the details in the midterm. I will put up solutions to all the tutorials. I will aim for by the end of Friday this week. That is my goal. I got flu over the weekend, so that didn't help. Okay, anything else? Anything else that I've forgotten? Yes.
If we send it to Gabriel, usually by email, should we send it to you now?
Yeah, so please don't send anything to Gabriel, just send everything to me. Send your tutorial solutions. Remember, they need to, all tutorial solutions need to be in by 6 p.m. on the 9th of December. That is the hard deadline. If you want it graded so that you can actually see how you did, then obviously get it to me before then, since the midterm is on the 9th.
What's the homework exercise thing for this week?
That is a great question, and as soon as I get home tonight, I'll figure it out. Yeah.
Do you know if you have Gabriel's, I mean the submissions that we give to Gabriel, do you have them or does he have them?
So the hard copies,
Yes.
he must have them. I will check if his colleague can access them. Okay. Would you mind just sending me an email to remind me to do that?
It's not really important.
Okay.
If you have them, it's available.
No, I don't have them. All right. Let's just take a moment to get focused. If you feel comfortable, close your eyes. Otherwise, just look somewhere not too stressful. And listen to the sounds around. And gradually bring your attention to your body. Feel your feet on the ground. Feel your body on the chair. Sit up straight enough so that you can get oxygen into your lungs, but not so straight that you're uncomfortable. And just bring your attention to your breath. So start noticing the air as it comes in through your nostrils. Notice how your chest and your belly expand as you breathe in. Notice that between breathing in and breathing out, there's a still quiet moment where your body just rests. And notice as you breathe out, shoulders, chest, belly all relax. So for 3 whole breaths, just notice your breathing. See if you can notice all the ways your body changes as you breathe. And if your mind has wandered off, notice where it went, and bring it back to the breath. 2 more breaths, just breathe. That's all you have to do right now, just breathe. One more breath, just breathe.
hey.
I was in the
Alright. So just trying, despite interruptions, to keep the momentary calm. Let's make a start. You can open your eyes if you manage to not open them. Alright. So we are heading into the final stretch. What are we doing today and Thursday? Well, actually this is just for today. So we talked about line integrals last time. So we said, what about if you want to integrate sort of a one-dimensional function, or possibly part of a surface, along a line that isn't one of the axes? So basically extending the notion of we were talking about in Calculus 1, you talked about integrals of one variable, and now we're kind of letting the line along which we integrate vary. So we talked about that. Of course, now we might want to do something in 2 dimensions. So up to now, when we've integrated, we've had kind of a surface, and we've had a flat space, and we've had some area on the flat space, and we integrate the surface over there to get a volume. Okay? Well, we can play the same trick that we played with our line integrals and say, what if we don't want to integrate over some flat patch? What if we want that to be some thing that moves or has a kind of 3-dimensional shape? So it's just, again, extending what we know to slightly more abstract situations. So that's our surface and our surface integrals. And then we're going to talk about oriented surfaces, which is something that we're going to need a little bit later on. The basic idea is that there are some surfaces where you can define a particular direction on them. And those are the kinds of surfaces we want to work on, because we're going to want to talk about curves on surfaces. And remember, when we're parametrizing, the direction, we have a direction in a parametrization. So we need some way of talking about surfaces that allows us to do that in a kind of consistent way. So that brings us to the end of chapter 15, which is really all the kind of background that we need for the final bit of the course, which is getting us to Maxwell's equations. So chapter 16 is really pulling together everything that will take us to Maxwell's equations. We're going to talk about, so we've already seen the gradient, we're going to talk about it a little bit more, and then we're going to introduce 2 other kinds of derivative. So we think of the gradient as a sort of derivative-ish sort of thingish. But it turns out that there are more derivative sort of thingishes, the divergence and the curl, and they're useful in their own ways. Then, of course, it wouldn't be a course of MSP if we didn't talk about identity. And then we're going to come to Green's theorem in the plane, which is actually one of, in a sense, one of Maxwell's theorems, Maxwell's equations, but it's more general than that. And then we're going to talk about that in the plane, so for functions of 2 variables, and then we're going to look at it in functions of 3 variables. And that leaves for Thursday just 2 final things. We're going to talk about Stoke's theorem, which you might have heard about. Okay, we're going to finally get to Stoke's theorem, and then the final thing we're going to talk about is actually Maxwell's equations, and see how everything we've done this period leads us to being able to understand Maxwell's equations. Okay, so the end is in sight. Right, keep going, push through. All right, eat chocolate if you need to.
You don't need to say that twice.
I don't know. I don't for myself, but some people need reminding. It's strange. But yeah. All right. So, surface integrals. So, all right. What do we got? Parametric surfaces. So far we've only had parametric curves, but it's fine, right? How do you define? So remember we talked about curves being parametric. Well, you can imagine that you might instead decide to describe some surface which we've previously described as like z is equal to x squared plus y squared. Maybe you can describe those parametrically too, and it turns out that you can. So if you think about it, if you're describing a curve, you need one parameter, you need a time variable. But if you want to describe a surface, you're going to need 2 parameters, because you need to have this kind of concept of not only this direction, but probably also this direction. Okay, so we can describe a parametric surface in 3 space as a continuous function. And basically what we're doing is we're saying, okay, these are our parameters. So previously we only had a t parameter, but now we're thinking of 2 parameters, a u and a v, which kind of marks out this. And for each point there, we can think about what the position on our surface would be based on the values of u and v. So previously what we had was we had a t like that, and that mapped us to some, what do we call it? I think we called it S of t. And that mapped us to some S of t either on the xy plane or the xyz. Okay? Now we're taking, instead of having a t, we've got a 2-dimensional grid. So we're getting, for each point in here, we get 2 parameters. And we take those 2 parameters and we plug those into our equation, our r, and that tells us where we get our point on our surface. All good? Okay. So let's just try and think about this. Here's a parameterized surface, a cos u sine v in the I direction. Take a moment to think about what this surface would look like. So maybe plot some points, discuss amongst yourselves, see what you think. Any suggestions for what this might be? Hmm? Okay, it might be wavy, it might not be wavy. Sounds quantum. How might you figure out what this looks like? GeoGebra, good answer.
You've got all a bunch of points, but that's probably an easier way. I don't know.
I mean, I would probably plot some points, or at least think about it. Okay, so let's think about just the x component. How does that vary? What is the maximum possible value of the x component?
-1.
Careful.
A to minus A.
Right, so, okay, so we've got an x that's varying from a to minus a. Okay, and in fact the same must be true for our x, y and z components. Alright.
But z is always positive, right?
Sorry?
Isn't the z component always positive?
Well, let's check. Okay, justify your answer. Justify that.
Because v is only between 0 and pi over 2, and
Aha.
all of that area cosine is between 0 and 1.
Nice. Okay, so these two, our y and our x, are varying between minus a and a, and our z up here is varying between 0 and a. Alright. What else? is a half sphere. Very nicely done. How do you figure that?
Because if you look at the XY plane,
Mm-hmm.
it will be defined between minus a and a, and for the test it's always 0 to a.
Mm-hmm. So I think what we can take from there a little bit. So you could say, all right, let's hold one of our parameters constant. Maybe let's let this one equal 0, and let's see what we get if we just let u go through everything. Okay, so if we let this equal to 0, then what happens to this term over here? That's 0. Whoops, that's 0. Okay, that's not a good number to pick. All right. Okay, let's take pi over 2. Right, so if we put in pi over 2, what's cos of pi over 2?
0.
Okay, so this term is 0. What's this? Oh, sorry. Cos of pi over 2. So, okay, but what is sine of pi over 2? 1. Okay, so each of these terms is 1. So when this is equal to pi over 2, we really just got this term is 0, and this is a cos u I, and this is a sine u j. What does that map out? A circle. Okay. And then you can start to see, well, if I change my sign, so if I change my nu a little bit, my sign is just going to decrease, because that was at its maximum value, it was 1. It's going to be smaller, but we're still going to carry on having our circles. They're just going to have decreasing radii, and that's happening as we decrease this between 0 and 1. I mean, between 0 and pi over 2. So basically we must have something doing this. So it's a sphere, or the top half of a sphere. Okay. Ish? Yeah? Alright. So, now that we've parameterized our surfaces, this gives us a way of talking about surface integrals. So our idea is basically exactly what we've done many, many times before. Let me find the picture here. Where's the picture? Okay, we want to be able to basically integrate some surface over some other surface. So not over a flat bit, but over this surface here. What do? We do like we've always done when we're trying to do an integration over a surface. We divide it up into squares, we work out the little volumes, and we add them all up. I could go into excruciating detail, but you'll be glad to know that I won't. You can read through this. It's just technicalities that I have to put in. It's the terms and conditions. But basically, it's the usual physics assumption that we're going to make, that everything is nice and smooth. There are ponies. It's fine. Okay, so where are we headed? The kind of thing we want to be able to answer is, we want to integrate that bunny z over a conical surface. Okay, so we've been used to integrating things like that over something on the xy plane. Now we don't want to do that. We want to integrate that over some conical surface. There's no reason why we can't. I mean, we're still finding a volume. It's just that the bottom of the volume isn't the flat bit that we're used to. It's some other bit. That is all we are doing here. So you can read the details. But essentially, all we're doing is, if we want to integrate, so we know how to find the area on a surface, we've done that before. If we want to find the volume, we put the function that we want to find the volume of, and we've got to do some kind of coordinate transformations to give us the surface element that we're looking at, because we're not looking, so if we were just doing this over the flat surface, we would have f dx dy. But now we're doing it over some curvy thing, so we need a surface element for our little dA, And it turns out that our surface element looks like this. Which actually mightn't look that weird if you go back and have a look at when we talked about just general coordinate transformations. We learned how to do this. We learned how to go from a dx dy to some surface element in a different coordinate system. So we have actually seen this before, it just looks a little strange. And if you work through all of this, so here we're assuming that we're in XYZ, we're not talking in spherical or polar coordinates, you end up with this thing. I'm not spending a lot of time on this, except to say we'll do an example. Basically, all this is an extension of our ideas of transforming coordinates. It's like you're going from living in flat space to living on some surface, and so you change your dA from your flat space into the equivalent dA on the surface. Yeah.
Why do I multiply with the length of the cross product of the two derivatives? Where does that come from? Like logically speaking.
Logically speaking, where does it come from? It comes from what we need is that ds, and what we're getting is a normal vector, which enables us to kind of figure out the orientation of the surface element relative to the actual surface we're trying to integrate. Okay, I'll put some pictures in. So yeah, a good question. So we're finding our normal, which is dr cross dv, which is this thing, which is how it ends up over here. Let me just see. I think the textbook might have a nicer picture that I didn't put in. Where is the picture?
Isn't that the same thing we do with calculating the normal vector of the tangent plane? We also
Yes. So that's exactly what we're doing. Is we're kind of calculating. We've got our crazy surface here, and we're calculating. We're thinking of it as a little flat bit, a tangent plane, and it's a very small bit, so it's a good enough approximation to the part of the surface. Yeah. Okay, let me go to the textbook page 919. Come on, yeah. Okay, here is kind of the picture that we're looking for. So we would usually look over a dA that looks like dx dy, but because we're actually wanting to integrate over the surface here, we need to kind of transform this dx dy into this little patch over there. And in order to do that, you can imagine it's not always going to be like flat like here. It might be like this, so you've got a kind of distortion happening, and it's got a different orientation, so we need a normal vector that's going to tell us about this a little bit here.
And the area of that will also be a unit area, one square unit. Even though it's going
Yes,
to be
in the coordinate system of S. Yeah. Yeah.
But I wanted to ask, so it's more of a logical question, but once we integrate it, what's our end result? Like, what's
what do we actually do?
Our function, what do we get at the end?
Well, let's do one and see.
Okay.
All right. So here's everything that you need. Right, everyone got the problem written down? Because I'm just switching over to GeoGebra so we can have a look at what's going on. Alright, so what have we got? So we've got a surface, that's our cone, and we want to integrate z over this cone between z equals 0 and 1. So let's put in we can do something. Alright. So we've got our cone, and we want to integrate over the surface from z equals 0 to 1.
So inside, or what it does over the surface?
So it's our surface, and we're integrating. So if we go back to what the thing is that the thing we're integrating is the value of z over that surface from z equals 0 to 1.
That translates into volume.
Yeah.
Under, between those planes, inside the cone.
Yeah.
Or around the cone.
Inside. So let's work it out.
So we still get a volume even though we're not doing it in respect to x, y directly?
Yes, exactly. So we are, I mean, it's like we could get one volume, say this is my xy plane, and here's my crazy surface. I could get this volume here. But maybe I want to do something else. I want to have this surface here and get the volume between the two surfaces. Yeah. Yeah. So it's kind of, but it gives you much more generality than taking one integral minus the other, which is another way that you could do it. And it's going to lead us to being able to integrate vector functions as well. Woo! All right, so if we think about this integral that we're doing over here, we need to express this ds, which is kind of like our little dA. So we need that in terms of things that we can integrate. We can't integrate ds's because that's in 2 dimensions. We want to change it into like something like a dx dy so that we can split up our integral and actually do it. We have the way of doing that. So let me see. All right, we want to have a look over here. I'm just thinking the best way to do this. Well, let's start out by going, what does our ds look like if we're, so this is our ds. If we plug it into this formula over here, what do we get? Well, what are our variables here are x and y. So instead of using v's, you've got x's and y's, but that's fine. We have to deal with that. So we need this bit here. So we want dz by, I'm just making sure I get this right. Wait, have I done this wrong? Okay, I think I put in a simpler example than we needed. Okay, so the way that we're going to tackle this one I had a very good reason for putting this example in, I can't remember what that reason was.
Is it so we can parameterize Z?
Yes. I'm just trying to remember.
Oh.
All right. Okay, so what we're doing is we need to find our surface element on our cone because we're not integrating over that. So let me write down what we get and we'll see how where does this come from? Sorry, I'm just going to check the textbook because I'm blanking. Oh, don't. Okay. All right. All right. So this is our cone, our surface that we're looking over. And so we want to look at dz by dx and dz by dy and dz by dz. Going to need those. All right. So dz by dx on our cone. So this is to find our area element. Dz by dx.
X over Z.
Okay, and dz by dy.
Same thing. So Y over Z.
Okay, and dz by dz.
1.
1. Okay. So what we end up with is see if there's a okay, so there is a formula that I didn't put, which I should have, which would help.
Without the formula.
So you can get the formula from this one, but it's going to be simpler. Yeah.
Maybe I'm stupid again, but if you derive z with respect to x, like how do I get the divided by x? Z.
Because it's just square root of x squared plus y squared.
So
this is like
they're substituting in z because you'll have x over the square root of x squared plus y squared. So they're simplifying it and they're saying it's over z.
Okay. I see. Thanks.
okay.
back in the previous tutorial.
Gibt es nicht U-Manager? German was very
All right, so I will put the neat version of this, but essentially this thing is the most general form where you have some surface that is parametrized with u's and v's. But sometimes you might have your surface parametrized with x's and y's, and you wouldn't want to go the whole hog, which is what we've got over here. In which case, we've got this simplified version. You can get from that to this. And we, in fact, although you might not remember it, did something similar when we were changing coordinate systems previously. But the basic idea is, so if we've got some surface integral of x, y, z over some surface g, so we're integrating this bunny over g, then this is the kind of the little dA that we get in our x and y from the fact that we're integrating over our surface g rather than our flat domain. Okay, and remember our g sub 1, that's the first derivative of g, so the derivative of g with respect to x, derivative of g with respect to y. Okay. Yeah.
So the reason we don't have this here is because we integrate between two planes that are flat on x and y, like parametric is working. So what? We don't change to different coordinates?
So we're not changing it to different coordinates because, in fact, our surface is parametrized with respect to x and y when it's not parametrized with respect to a u and a v. But you could reparametrize this in some crazy way. I mean, since it's a cone, you might want to parametrize this with respect to r and theta, in which case you would go and use that full thing up there, but for the moment we're not doing that. We're just keeping it parametrized in terms of x and y. And we don't think of x and y as being parameters, but they are. Does that help a little? So for this purpose, we can use this simpler formula over here. Yeah?
Sorry,
Okay.
what you're saying.
No, it's fine.
So this is a level of complexity down than the one you showed before, but we could kick it up a notch and express x and y in u's and v's.
Yes.
But we won't.
But for right now, we're not going to do that.
Being.
Yes. So that was why I put this in. I just forgot to put the simple formula in first. Sorry.
And if I calculate square root of 1 plus blah blah blah, then that should be 1 because our integral should be just f of x, y, z, dx, dy.
Sorry? If you calculate...
Like basically now if I calculate the square root of this whole thing, like should that give me 1 so that basically equals 1?
Not quite. Sorry.
But then how is this like, because I thought in normal coordinates we should stay there, I can just express ds or dA as dx dy and then I'm done.
So, well, you can. I mean, in normal coordinates, if you're integrating over an area on the xy plane. But now we're actually integrating over this cone, so we still need to change because the little dAs on our cone are not going to be the same as the dAs here. But we are expressing these dAs using x's and y's, but they're not going to be the same as like a little, if we sketch so here's my little dx dy, but if I imagine now I've got my cone sitting somewhere here and I've got a little thingy here on my cone, I can still express this area element in terms of little dx's and dy's, but it's not going to be just dx dy. It's going to be kind of warped, and we kind of need that transformation factor, and we're about to see what it is.
That's the square root.
And that's going to be given to us when we work out So this distortion factor will be given by this thing over here. So let's work it out. Okay, so we are in a situation where, in fact, we just have f of x, y, so we're not looking at this. So we're good to go like so. We've got our dz, and this is our g.
Quick question.
Yeah.
If we did have the z, would that formula still apply if we added a g3 of x, y, z squared?
So we would still use this formula, because this bit is giving us the distortion on our surface. It just happens that we're not integrating a function of 3 variables. We're just a function of 2 variables. Yeah, so this still works. It's just that we've changed our z. Okay. So, phew, okay. So let's look at our ds, which is this bit here. It's going to be 1 plus, we need the square of the first derivative, so we need the square of that, plus the square of the second derivative, so we need that. And then we just need dx dy. So all this is really saying is that when you go from being this little area over here to being a little area on the cone, you need this as a kind of translation factor, a scaling factor. But this actually looks kind of hairy and you wouldn't want to integrate that. But we know that z is equal to x squared plus y squared. So let's just make this look a little bit better. We've got 1 plus x squared plus y squared over z squared. But x squared plus y squared is just equal to z squared. Z squared over z squared, so long as z is not equal to 0, we're good. And we're going, well, we're not worrying about z being 0, even though it's one of our limits. So this just gives us root 2. Because we're thinking about the small little elements. So what this says is, if you want to translate from a little dx dy that would be lying on the plane to one lying on the cone, you need a factor of root 2, and that is how your little area distorts. Okay. All right. So plugging that all in, what we end up with is our integral over s of z ds. Now we plug in what we know. We've got our root 2, which is just a constant, so that can come out. So it's the integral over the cone. So that's x squared plus y squared is less than 1. So all I've said over here, I've just thought about what this means. I need my cone to go, so I need to go from 0 to 1. So I need root x squared plus y squared to lie between 0 and 1. But I might as well just make my life easier and say I'm going to integrate between x squared plus y squared, because I could square that. So let me finish writing this down and we can look at it. So all I'm integrating, all I'm doing when I integrate here is saying I want to integrate over x squared plus y squared is less than or equal to 1, because it's automatically going to be bigger than 0. I'm integrating this thing. I've taken my root 2 out, which is the factor that puts me on the sphere, and now I'm integrating over this. Yeah.
So since the x squared plus y squared is smaller than 1 as a disk, could we write that in terms of polar coordinates, and that would also
Yes, that's exactly what we're about to do. So we look at this and we go, we're integrating z over a disk. And life integrating over a disk is better if we do it in polar coordinates. So let's switch over to polar. So we're integrating over the disk from radius 0 to 1 over the whole disk. So we can rewrite this in polar. So remember, going from dx dy to polar, we go to r dr d theta. What is z? Well, if we look back to what we've got over here, we could rewrite this as z squared is equal to x squared plus y squared. So really, our z is just acting like our r. So we end up with an r squared here. Integrate r from 0 to 1. Integrate theta from 0 to 2 pi. And if you work out those integrals, you will get 2 root 2 pi over 3. Which is the volume.
So we converted twice.
Yeah. Yep, we just snuck in another little, because it's so old hat now. And in a sense, this r dr d theta that we used over here to go from here to here is using the same idea as we used up there to find the dA ds conversion. Right.
So could you go through it once more?
Sure. Okay, let me just. Yep.
Wouldn't that value change according to the units you're using? In the sense that you also have to adapt in real case scenarios to the units you're using in your scenario where you won't have
So
it won't translate one to one.
So if in real life you need to include in your factors that will convert your units for you. There was another question? All right, well, let me go through it one more time.
Can I just ask something?
Yeah.
Quickly? So you say that the z squared, or like the z is working as r squared, right? But don't you have like an extra r, or is that already like included in the r dr d?
So, okay, so let me go through it.
Okay. Yeah.
Okay. All right, so what did we do? We want to integrate z, whatever z is, over our conical surface between z equals 0 and 1. And life might be simpler if you just worked out the area of that cone, I mean the volume of that cone, and moved on, but we're going to do it the hardcore way. Okay. So we have this general formula which says if you want to integrate either a surface or a volume over some surface G that is not your flat plane here, you have the thing that you want to integrate, as you might expect, but then you need a little kind of converted element which takes what would be a little square on the plane to whatever little equivalent square in its distorted form on the surface that you're interested in. And that's what this bit over here gives you. So, and this is when you've got everything, the thing you're integrating and your surface that you're using to integrate is in x and y's. That gives this formula. If, in a more complicated scenario, you had things parametrized, you would use that formula up there. But you can see there's a lot of similarities going on. You would just take a bunch of derivatives with respect to other things. Okay, but we're keeping it simple for the moment. Okay, so because we're working on our cone, we need to find our little area, our little ds, our little area bit. We plug into this formula. So we took our derivatives up there, we squared them, we took the roots, and we discovered delightfully that it's just root 2. Okay, so this root 2 dx dy is a little elementary area patch on the cone, which kind of relates in size to the little square that you would have dx dy on your plane. Okay. All right, so then we plugged it all in, and we got this. well, we got this, and we got this, and then we thought about what is it that we're actually integrating over. Well, we're integrating our cone, so we're integrating from x squared plus y squared equals 0 all the way up to 1, because that is what z is, well, z squared is equal to. So we're integrating over that kind of disk on the cone. And looking at this bit over here, we said, well, that's a circular patch. It's much easier in polar coordinates. So let's switch to polar. So if we want to switch to polar, we have dx dy goes to r dr d theta. Okay, so we got, so converting our dx dy, we got an r dr d theta. And then we needed to convert z. But if we have a look at, in terms of polar coordinates, looking at what we've got over here, our z is just equal to r. So we got another r coming along. So we got an r there, which just gives us our r squared. And then we need to think about our limits. So if we're integrating with respect to r, we know that our r is going from, our radius is going from 0 to 1, which is what our z was doing, and our theta is going the full revolution. Okay. Yeah.
Why did you put d theta in the first integral and the second one?
Because I find it really hard to write that. Because I grew up writing all my drs and d thetas at the end.
Yeah.
It was just muscle memory, sorry. Yeah.
Shouldn't the r be square root of r then?
No, because remember for a circle we have r squared is equal to x squared plus y squared, and what we're looking at, I mean, we're integrating z.
Yeah.
Yep. Yeah. All right. Okay. We will do some examples in the tutorials. Okay. I think the key thing to take out of that section, I mean, you could go into a lot more detail, is the idea that we're just trying to figure out how to integrate stuff when we're not on the xy plane. We're thinking about integrating stuff with respect to some surface. Okay, so the next little bit is just some concepts that we're going to need for the final bit. It's the idea of an oriented surface. So what we're going to need to be able to do is talk about clockwise and anti-clockwise curves on surfaces. And that means that you need to be able to have some way of defining what clockwise or not clockwise means. And mostly this is not going to be a problem. We're going to have what are called orientable surfaces. But you might ask, well, what is an orientable surface? It's easier to talk about what is not orientable. All right. So you've seen a Mobius strip. So you take a piece of paper and you do one twist, and then you join the ends together, and you can follow. So if you imagine, so this is a Mobius strip. Imagine, so we've got our little crab. He's kind of in the surface. So he's not on one side. He's in the surface. If he comes up and around and then down and then goes back up, what happens is he's flipped over in this crazy surface.
Why is it a crab? Is there some joke behind that, or
because Wikipedia gave a crab.
okay?
And who knows? Okay. The point is, this is a fiddler crab. A fiddler crab has one bigger pincer. So when he does this thing, you can see that over here, his pincer was on this side, and by the time he gets over here, it's the same pincer, but he's now... Okay. So the problem with this, and you can, and then if our fiddler crab kept going, the next time round he'd be back in that orientation. So there's no actual way that you can decide kind of this looks like it should have two sides, this surface, but it doesn't. It only has one. Okay, if you like knitting and you would like a pattern for how to make a Mobius scarf, I can also give you one of those. Okay, and you can imagine things like this would be, so suppose you tried to integrate on this surface. So we've just talked about integrating over a surface, and it was fine because we knew exactly where the surface started and ended. Well, where do you start here? And where do you finish?
Isn't it the case, like, you can treat this as where you need to do double to end up in the same place?
But the problem is then you're still kind of, so where we're headed with this is we're thinking about, we want to be able to integrate vector fields coming out of this. If you did that, you'd kind of get twice. And it's also not at all clear which direction you should go in. So we want to avoid, basically, this is the kind of thing we want to avoid. We want to just have a nice surface that we can look at and we can go, that's my surface. If I follow some descriptions, I can define an up, I can define a down, I can define a counterclockwise, I can define a clockwise. Whereas with this bunny, okay, so this leads us to the idea of orientable, and the official definition is you can find a unit vector field defined on your surface that varies continuously and is everywhere normal to S. In practice, what does this mean? It means you don't have a situation here where you can take some object on the surface, move it around, and have it end up back where it started, but flipped. In terms of thinking about a vector, so if we think about a unit vector field, we want to define it, so we're thinking about lots and lots of little normals all sticking out of our surface, and we want to be able to define that everywhere, and you would have a problem with that here, because you would define a unit vector, maybe you'd start over here and you'd define a unit vector coming out, and that would be fine, and you'd keep going. But the problem is you'd get back, you'd be on the other side, and now you'd have two unit vectors, they'd be pointing in opposite directions. And it's not, like, that's a problem. Okay. Alright, so that's orientable. Why do we care? Because now, if we've got some surface, we can start to talk about orientation for curves and things that we're going to integrate around. So we've got some surface M, don't worry, just smooth, and we're thinking about some curve on it. And if we're oriented, now we can say, well, we know because we're an oriented surface that we've got our little normals, we can define them. So let's take those normals, and we're going to use them and say, all right, if you're a curve on the surface, then I'm going to orient my curve so that my normals are always pointing up on the left. So if I want to walk around this curve in my correct direction, I'm going to define it so that I look at my normals and I go like so, and that gives me a way of going around this curve. And you might have a surface with a hole in it, that's fine. What will happen on the hole? Well, again, you'll say, okay, I'm standing, here's my hole, I always want the normals to be on my left, so I'm going to walk around this way, so we end up going anti-clockwise round, clockwise round holes. Strange but true. You wouldn't be able to do this if you couldn't define your normals. If you weren't orientable, you couldn't kind of give a direction to curves. And then life becomes much more complicated if you want to integrate. So that's why we're talking about...
Is the direction through the hole always needs to be opposite to the direction around the surface?
Sorry, say again?
Is the direction that you're going, like, through the hole usually opposite to the direction you're going on the surface?
Yes.
Why?
Because you always want your normals, your normal P is pointing on your left. So if you think about walking, which direction do I walk around this curve to make sure that they're on my left?
So So that basically you don't integrate the surface inside the circle, but the one outside, kind of like that?
That's where we're headed, yeah.
Then for non-orientable surfaces, can't we just break them down into its orientable parts and then add it up?
Possibly. I think there are complications there. I mean, it's not so. Non-orientable are weird because it's not clear how you would break them up. And even, I mean, so I agree that you could split a Mobius strip up into constituent bits of paper and integrate over those. But if you think about it, the original thing wasn't orientable, so it's not clear whether you should treat. So, okay, here's my split up Mobius strip. It wasn't clear from this which was up and which was down. I split them up and I can certainly define an up and down, but now I've kind of added information which I didn't have initially.
Oh, so you don't have its original part anymore?
Yeah.
Yeah. Okay.
Yeah. So coming back to the whole, just imagine that you've got all these vectors of field, are trees pointing up, and you want to walk around the lake so that the trees are always on your left. Maybe that helps? Okay. Strange but true. This bit, which is not, is just to kind of say, okay, what if I have something like a block? This is not smooth because it has curvy pointy bits, but I can break it up into smooth chunks, and we say that we can think of this, the surface of our cube, as orientable if I can split it up, and whenever I have a boundary of two smooth surfaces, orientation is going to give me that curve will go one way, this on, if I'm thinking about this bit, and the opposite in its joining bit. Basically, what you're thinking about is you always want to have your normals pointing out, and if your normals are always pointing out of your surface, then this is the orientation that you're going to need to keep your normals on the left. Okay. I wouldn't get too hung up on this. Pretty much everything we deal with behaves like this. Yeah.
Is it then impossible for a continuous curve to have normal vectors going in opposite directions?
How do you mean?
Because if you have a cube and it's broken down into two surfaces, and you have normal vector going up and one going down on opposite sides.
Yeah. I mean, so down here, it would be pointing out down there.
But then if you have a continuous curve where there are no nasty points.
So if it's a continuous surface with no nasty bits, and it's orientable, then you need to be able to put your normals out like fur all over nicely. I'm not sure if I'm answering your question. Okay. All right. Okay, so this I think okay, so what I want to talk about from here, you might have been wondering, like, why are we talking about this orientability? So imagine you have a vector field. So we're thinking like something like a magnetic field, okay, maybe from a point charge, and we have some sphere around it, and we want to work out kind of how much electric field or magnetic field is going through that sphere. Well, you might guess correctly that we need to do some integration. But what's important is because we have a field that's going in a particular direction, we need to be able to talk about the surface of the sphere in an oriented way. Are we thinking about the magnetic field that's going out, or are we thinking about it going in? We want to be able to think about our surface and talk about an up or a down, an in or an out, or rather, an out or an in. Yes. Okay. And so this kind of question here is why we needed to talk about orientation, because we need to be able to say, okay, I've got some flux, I've got some field, it's a vector field, okay, and I want to think about how much is going upward through the part of the surface x squared, y squared, lying wherever. So I'm thinking about how much is going up. I want to measure just how much is going up. I could equivalently have asked how much is going down, or how much is going in any other direction. But in order to be able to specify that direction, I need an oriented surface. So that's kind of why we needed to think about this. Okay, so we're thinking about how to find, so flux is the amount of vectors going through a particular surface, the amount of a vector field. But I think we can actually come back to this within the context of the stuff that we're going to do in a bit. So let's leave this for a moment. Okay. So all of that stuff was just the last few tools that we needed for our final section, which is talking about vector calculus. Like, hang on, I thought we talked about vector calculus, but there's more. Okay. So what is the most fundamental, hint, thing that you learnt in calculus of one variable? It is the fundamental theorem of calculus, which basically gives you these two bits, which say, if you have, so there's two bits that you might think about. You basically have this idea of a function and its derivative, and the kind of the link between the two is, if you have some little function and you integrate it from a to x to get some big function f, then this f is differentiable, and the derivative of this bunny is that bunny. So it gives you the link between integrals and derivatives. That is kind of the important thing. And similarly, the second part of the fundamental theorem says that if you have any antiderivative of this bunny here, and you're integrating between set values a and b, then in fact this integral is the same as just saying your antiderivative at b minus your antiderivative at a. And you don't even think about using this, but you do it all the time. Every time you integrate, you're using the fundamental theorem. So far, we haven't seen anything similar in multivariable, but you might ask, is there something similar? And the answer is yes, and it's incredibly rich and really gives us, in some sense, Maxwell's equations. We are going to look at in 2D and 3D separately because they're not quite equivalent. But, all right. Let's build up what we know. So just remind me, because this was something that happened in the test. If I'm a surface, so I'm an f of x and y, what is my gradient? Okay, so, and that would be partials, yes? And what does that tell me again?
At any given set point, what is the direction for maximum change of z with regards to the I and j unit?
Thank you. So this says if I move in the direction of gradient f, so along the xy plane, the resulting change that I have in my f is the biggest that I could get. Okay. All right. Now, if I am a volume or an object, so I'm an f of x, y, z, what's my gradient?
Same with the partial derivative for z.
Right. Okay. Thinking in terms of fields, basically what our gradients, whether you're in 2 or 3 variables, tell us is how a scalar field changes. So we're thinking about, for example, in 3 dimensions, we're thinking about the temperature in a room, and at a particular point, if you find the gradient and you go in that direction, that will be the greatest increase in temperature. Okay, so this is a scalar field. It's just a temperature. So what we'd like to think about now is what is the equivalent concept if we have a vector field. So I've just made a note here. Okay, we met the del operator. It looks like that in the 3D case. But we are thinking about, for vector field, so remember vector field, put in a vector, get out a vector. Okay, what are the equivalent, what is the derivative of this crazy thing? The derivative for whatever that is. And things suddenly look a lot more hairy. Okay, because remember a vector field has 3 components, and each of those components depends on x, y, and z. Each of these is a scalar field. So if you think about all the possible derivatives we can take, there's a lot of them. Okay, so for each component, there are 3 partial derivatives I can take. Yeah.
So could I think about this? In what direction would I have to go to experience the largest increase in wind, basically? So I'm looking at a wind blow that has a direction and a magnitude, and I'm looking for the strongest wind blow.
So, I mean, that's the kind of question you want to ask, but it's not clear how we would even define that yet. Okay. I mean, so our gradient is very nice. It says put df by dx by I, df by dy by j, and that will give you a direction. Mm-hmm. But if I look, I've got 9 partial derivatives. Where do I even begin?
Mm-hmm. So what is this then?
So at the moment, this is nothing. This is just me listing the partial derivatives. Okay, I haven't given you a mathematical thing yet to work with. And the thing that was kind of realized was that there is no single equivalent thing like the gradient that captures all the information that you might want. So we will in fact look at 2 different things using derivatives that capture different aspects of the change that we might be interested in.
But isn't that the Jacobian, kind of?
Well, I mean, I've just put stuff in a table. Probably, yeah. I mean, if I turn this into a determinant...
But does that have any meaning?
It does have meaning.
But not with regards to...
Not with what we're... Yes, but not beyond this course.
Yeah.
Beyond the scope of this course. Yeah. Okay. So we want to pull... So each of these little bunnies here has some information. But we'd like to pull the information from those 9 things together into something useful like the gradient. As I've just said, there are actually, you can't do a single thing that gives you all the information. There are 2 things. These 2 things are called divergence and curl. The divergence is going to give us something which feels a little bit like gradient. Okay? And it's defined as taking our little gradient operator here and dotting it with our vector field. Okay, so this is not the same. So we've already seen del f. That is not the same. Here we are treating our little nabla as a vector over here, and we are dotting it.
It's del f times f.
Sorry?
Del f dot product with f.
Yes. So we'll see. So if you think about how that, let's look at that dot product. Remember our del is and we're going to dot that. So if we do dotted with f, we're dotting this with then if you remember your dot product, it says this is going to give us a scalar, so it's giving us one number. Okay, and well, rather, it's not giving us one number, it's giving us a scalar. So it's going to take dx by fi, so that's this term over here. And then it's a dot product, so we just add to the next thing dy times f2, so that's this bit over here, and dz by f3, which is this bit over here. Okay, so that's the first thing, and we will look at what the divergence tells us, but we're just defining it first. Yeah.
So when you said what the divergence was, you said something similar to a gradient.
Mm-hmm.
Yeah, something more specific.
Hmm?
Like you just said, it's something similar to a gradient.
It is kind of.
That's kind of broad. No?
Yes.
Right.
I mean, so that is going to be our next section. Yeah. So yeah, it is broad. It's but it feels, you can kind of feel like there's a similar thing going on here to when we found the gradient. It's just the gradient is a vector. This is a scalar. So we need to understand what that scalar means. But something similar is going on. So that's the divergence. The curl is something completely out of left field. And it's not entirely clear why you might do this until we start looking at the interpretation of it. Now what we're doing is we're taking the cross product of our nabla with our f. And you end up with some vector given by this cross product. And I fully admit, it's, as I say, it's not clear why you would do this, but it turns out to capture very important information about the vector field that we need to know, which isn't talked about in the divergence. Okay, so those are just our definitions, and I wish I could tell you a nice story of how people came up with them, but basically people did some maths and physics and stuff and realized these were the definitions that made sense, which is how quite a lot of maths works. Okay.
Backwards? You were using them and then you realized, okay, so this is the little stuff you should.
Yes. So I was, over the weekend, I heard this great story about Heisenberg. He was doing a bunch of computations. He was like somewhere out, I think in the Swiss Alps, working hard on his thesis, and he basically came up with how to multiply matrices, but matrices hadn't actually really been, well, he didn't know that matrices had been invented. So he excitedly went back to his supervisor and he was like, look, I've discovered this thing, like I thought the maths was wrong and then I figured it out and here is this thing. And his supervisor was like, yeah, you've just discovered matrix multiplication. Well done, you. But this is an example of kind of the maths falling out of what it is that you're trying to do. So actually, and I discovered this also over the weekend, do you know why they're called matrices? Or why it's called a matrix? So,
something with Neo and
so actually, determinants were discovered first. I mean, you know that kind of the determinant comes out of finding roots and stuff. And then after a while, people discovered these square thingies, which when you did this thing, gave you the determinant. And they're like, oh, these square thingies are the mother of the determinant, and hence matrix, from the Latin for mother. Matrices are the mother of determinants. I kid you not. How weird is this? So again, the stuff you want to do kind of requires you to create the maths that you need. It doesn't always go but sometimes it goes in the opposite direction. Alright, Google, this is not super interesting, you just plug in, okay, you can find the divergence and curl. But what we want to talk about, probably, so I just want to kind of give you a flavor of where we're going. We want to talk about what is the divergence. Well, the divergence, if you like, is a measure of how much of a vector field goes, so So if you're thinking about at a particular point and you have a little sphere around here, you're thinking how much of my vector field goes through that little sphere if I make that sphere really small. That's kind of what we're thinking about. So it's a measure of the rate at which our field spreads away from that point. So in that sense, it's a little bit like the idea of the gradient. You're thinking about how your function moves away from where you are at that point. Okay, I will do more details on this on Thursday, but I want you to have a picture of where we're going. So we're thinking about how much, so we've got our vector field that's doing all its little spiky things, and we have this, the divergence is giving us an idea of how much it kind of points away from a particular point. But something else that you might want to think about is, do my vectors all point out in kind of directions like this, or are they doing weird curvy things? Is there kind of a rotation implied in my vector field? And that's what the curl gives us. So the curl gives us a measure of how much our vector field kind of rotates around a point. And those are going to be the two things that kind of turn out to be important for magnetic fields and stuff. Okay. Where do we go from here? We'll talk about curl. We'll talk about just a bunch of the inevitable bunch of things that if you're feeling bored you can prove using the product rule. You can totally just use the product rule, off you go. And finally, now that we've got those defined, we can start to talk about the theorems that we're interested in. So Green's theorem, which links, so now you might not see it, but this looks kind of like the sort of thing that we have for the fundamental theorem. So the fundamental theorem takes a derivative, it talks about a link between a derivative and an integral. And although we've both got integrals on one side, this is a line integral, and this is a surface integral. So we're still talking about derivatives and integrals. Weirdly. All right. Well done. I will put up the notes, and we will probably have another lecture on Thursday, same as we did last week. Okay, but this afternoon is a tutorial. Go to 0.001.
So for the
Normal tutorial time today, just different venue.